Welcome everyone to the last part of closest pair problem. In the first two parts, first we talked about the definition of the problem. So let's quickly go over. We're given n points p1 to pn. Each point pi is xi, yi, x coordinate is xi, y coordinate is yi. And the distance between 2 points pi, pj is just square root of sum of squares of their distance. Xi minus the difference between the coordinates, the usual Euclidean distance. And our goal is to find a pair of points pi pj that minimizes d pi pj. So we already saw about the problem, applications, and initial brute force algorithm, and then we tried with divide and conquer, and we faced the problem with combination. And then in last part we proved the structural lemma that if there are 2 points which are close enough in the combination part, then we just need to consider some constant number of points along some strip, constant number of neighbors along some strip. So let us formalize this in more detail in this part, and we recap the algorithm. So P is the initial set of points here. And what we do is we create Px and Py. Remember, Px is the points in P sorted by their x coordinates. Py was points in P sorted by y coordinate, which sorting will take n log n time. And then we recursively call this function Px, Py. This we pass, and we get the closest pair. The recursive function, in the base case, if we have constant number of points, we can just solve it by brute force in constant time. Otherwise, we divide and conquer. We divide into two equal parts, here q and here r, and then we saw last time how to do it in linear time. We create the points in q sorted in x coordinates, points in q sorted in y coordinates, and same for r. And then we can recursively call the function on qx qy with qx qy and rx ry. And then delta be the minimum distance here. So delta is the minimum distance of pair of points which are entirely lying either on left side or on right side. Now we have to do the combination. So x star was the maximum coordinate of a point in set Q. So this will have half points and remaining points are here. Then we claim, let's look at all points S which are within delta distance from L. So last time we saw this strip which is within delta distance from L. And for all these points in S, we can again in linear time construct Sy. The points can be sorted according to y coordinate. So we're not really sorting every time, but we have the list Py, and from that we can create this Sy by a linear path, which we discussed last time. Once we have that, for each point S in Sy, we compute distances from S to each of the next 7 points. So instead of all points, just next 7 points are sufficient, and that's a structural property we showed last time. And then remember what is the minimum distance among all these points in linear time. There are n points for each. We're just searching for constant number of neighbors. And then we remember these 3 values, and whatever is best, we return that. That's the algorithm. So the runtime becomes n log n time because it takes 2 times tn by 2. There are 2 sub-problems, each of size n by 2. And then the combination part takes linear time. So this recursion, if you solve, either using substitution method or recursion tree or master method, you will see it's n log n time. Now for this, you can read from Kleinberg-Tados chapter 5.4 or CLRS chapter 33 or Tim Ravgarden from chapter 3.4, and there are excellent video lectures. You can search many other, there are excellent other video lectures using Manim and very nice animations. For competitive programming, there is CP algorithms, which has a lot of problems related to closest pairs. You can have a look at them. And please practice problems from these books. Unless you solve problems, you will not understand a problem. Now, for a homework, I can also tell you, you can extend to other norms. So remember, we were talking about Euclidean distance earlier. And in that case, the function looks like this: xi minus xj square plus yi minus yj square root. But then, depending on the context, there are different types of norms which are defined. For example, this is called Manhattan norm, where we take the, instead of square, it is just absolute difference of these two terms, and then we add. In general, P norm is defined like this. You take pth power of this two term and then take 1 by pth power. And for infinity norm, you can take the limit and then whatever is large that will dominate, and then P and 1 by P kind of cancels out. So you just get the maximum of these quantities. And this also is known as Manhattan distance or taxi cab distance. For example, if I have a point here, xi yi, and this is yi, sorry, xi, yi, and xj, yj. Then the distance is basically in Manhattan distance or L1 distance, you look at xj minus xi, which is this distance, and then yi minus yj, which is this distance. So it looks like in Manhattan, we have this grid line structure, and the taxis follow to go from one place to another place. You have to take a horizontal path and then a vertical path. The distance along that, it's called taxi cab distance for that reason. And this is the formal definition of general P norm. Instead of 2-dimension, you can also do it for general dimensions. Here it's for n-dimensional vector, it is defined. So now you can also see the distances are different. Think of this is the origin. So this diamond shaped object, it's actually this boundary is L1 unit size ball. So all these points here, the distance from here is this plus this, and this is 1, or here it's 1, this is 1. So it's like it is 1 and this is minus, it's 1 0, this is 0 1, this is minus 1 0, this is 0 minus 1. Instead of L2 ball, it's a regular unit ball, which is like this. So Euclidean distance from any point on this circle is 1. For L infinity, this is this one. The maximum distance is 1. So you can check. And then once you understand the distances, then you can try the same closest pair distance instead of Euclidean norm. If we ask for L1 or L infinity, does it work? And how many points do we need it? Does it still work with 7 or fewer or more? And what happens in 3 dimension? And at the end, as I talk about some research problem, so this problem is a foundational problem in computational geometry. The area of computational geometry, this technique of divide and conquer, it has seen so much success from closest pair, farthest pair, convexal, Delaunay, and Voronoi, and Euclidean MST, many applications, which from brute force n square, we got n log n time algorithm. And in fact, this n log n is kind of tight. So in 1983 and 1989, Yao already showed that under some decision tree model, you cannot beat this n log n time algorithm. But under some other model, if you allow floor function and randomized algorithm, Rabin also gave an algorithm which is expected linear time algorithm. And then there are many other follow-up works, especially on approximate nearest neighbor. Then instead of 2-dimension, if you go to higher dimension, let's say log n dimension, if there are endpoints, what is the best you can get? And there are so many variants. It's Sosa paper in 25, JCM in 15, a lot of references there. If you're interested, just Google search this paper and check out status. Even in quantum algorithms, it's a paper by Scott Aronson last year. And quantum things are funny. And there is things like searching can be done for n elements instead of order n time and root n time. It's something called quadratic speedup. And this problem, in fact, can be solved in n to the power 2 by 3 time instead of n log n time, much faster for constant dimension. And this paper also talks about the previous history about the problem. So you can go over this Scott Aronson's quantum algorithm paper, though the techniques are quite different here. And it mentions the first paper is Bengless Samos is the divide and conquer based n log n time algorithm. In general, it's for d dimension 2 to the power d n log n time algorithm. Then this is the expected running time of linear time 2 to the power d linear time by Kuller and Matthias. And the lower bound is n log n by Yao under this decision tree model. And if we have the problem in higher dimension, poly log n dimension, then all the existing algorithm kind of give you a n squared time. The best algorithm gives you n squared time algorithm. And Karthik and Manuransi, Karthik is one of our frequent visitors in IISc. He showed it's kind of tight under ACTH conjecture. And yeah, there are several other connections of this problem to many other problems, as I mentioned, nearest neighbor and other problems. And I'll also like to mention one more fact, that this area of computational geometry, as I mentioned, it's a foundational problem. This is a textbook by Mark Debug. And Mark Debug will be visiting IISc in 2026. And the top conference in geometry, it's called Symposium on Computational Geometry, SOCG. It's also coming to IISc, first time in South Asia and Global South, it's second or third time. It's coming to IISc, of course, first time in India in 2027. So if you're interested in geometry, IISc and India is one of the top places to work on geometry, and especially IISc, we have multiple faculty work on computational geometry, including me, Rahul Saladi, Satish Govindarajan. So please email us if you're interested to learn about computational geometry. This is the best time to do CG in India. Thank you.